Alright, welcome to the AP Physics 1 Force Review Sheet solution. Here I'm going to go over section 1, which is number 1 through 10. Alright, so I'm not going to read the question here. You have number 1. The issue here is that you're going to notice that there is a person standing on a horizontal surface. So let me draw that for you here. Okay, that is our horizontal surface. Okay. And there is a person standing right there. Here is our person. And there's a force of gravity pulling down on that person. So here, force of gravity is pulling down on that person. Okay, so this is force of gravity. This is, and then there's a upward force supporting force from the wall, from the floor. So let me make that blue. And there is and this is from upwards supporting from the floor. So there's from the floor up. Okay, which of these two forces? All right. So the person is standing on a horizontal force feels two forces. Okay, and the person isn't moving. So notice that the person isn't moving here, right? He's standing on the horizontal surface, standing on the horizontal surface. So they have to be equal in magnitude and equal to magnitude, because this is due to to due to Newton's third law of action and reaction. So here that the object, that every single force has an equal and opposite force. So here we want to look at the force pulling on gravity. So that is this part, what I labeled as red, the downward pull of gravity. This is the force of Earth on the person. Okay? And then the blue one, which is the normal force, it is the upward supporting force from the floor. That is the force of the floor on a person. Okay? So here you would notice that these two are not actually reaction pair. Okay? So they are not action reaction pair. So do not form an action reaction pair. So the answer here is B. Some of you are wondering what would be an action reaction pair. So if this is the force of Earth on person, the action reaction pair, would be force of person on floor. No, person on Earth. So an action reaction pair is basically when you shift the noun. So watch. Okay. What you might see in your physics course is you see things like F1 on 2 is equal to force of 2 on 1. Same thing here. Do you see how they just switch the numbers? Right here, I switched the noun. Okay. 2. A person weighing 800 newtons step on a scale. This I meant to write right here. I meant to write 1,000 here. Okay. A person weighs 800 newtons step on a scale that's on the floor of an elevator car. If the elevator accelerates upward at a rate of 5.5 meters per second, what is the scale reading? Okay, so let's just draw the person here so we could get a visualization. Why can't I'm drawing? I'm drawing it all crooked today. Here's the person. Here's the scale. Why is it crooked? Here's the scale. Right now it reads 800 newtons. Okay, so that means if it's 800 newtons, this is the weight. Okay, the mass would be 80. Why? Because weight, the force of weight is equal to the mass times g. The weight was 800. The mass was your unknown. Gravity is 10. Notice if you divide by 10, you get mass is equal to 80. And you could say kilograms if you want to see the units. Okay? So here you have a mass of the person as 800 kilograms. And they are accelerating upwards. So the whole object is going, the whole system is going up with acceleration of 5 meters per second. Okay? All right. So here we know, here you could set up the force equation if you would like. And it accelerates upwards. So here you have the object accelerating upwards. Here you have mass times, we have here g plus the acceleration. Why? Because the object is going upwards. All right. So the net force is going upwards. Okay. All right. Okay. So the mass here of the object is 80. Gravity was 10. Acceleration is 5. Plug that into the calculator. You would get, this is 800 plus 40. So that becomes 1,200 newtons. Okay. Why? Okay. Because originally there is this force of weight, which is 800 newtons, and you're adding 400 more. This is the way. This 400 is caused from the additional acceleration upwards. Okay. It's not subtract. Subtract would be going down in the elevator. And where I'm getting this, if you want to see it before this, it would have been mg plus ma. Then you would have minus mg equals to ma, which came from sorry, just gonna write which comes from force of gravity minus force normal. Okay. Right. And this comes from F net equals to ma. This is Newton's second law. Okay. That's how I derived it. Normally, it's okay if you start here and just memorize it from here. That's fine, but you could see the deviation from there. Okay. Notice this goes to 0. Right. Okay. All right. So here we have a friction inclined plane for number 3. And with a length of 20 meters has a maximum vertical height of 5. If an object of a mass 2 kilograms is placed on the plane, which will find best approximate the net force it feels. Ooh, this is a very good question, and there's actually an easier way of doing this. Okay, all right, let's take a look. So let me just draw my inclined plane. Let's see, 20. Her height is 5. Okay. All right. So we have here. We have here what a vertical height, 5 meters. This is the height. And then you have a block which is placed what at a maximum vertical height. Okay, the mass here is equal to 2 kilograms. The whole distance here is 20 meters. Right, and again, if there is an incline, well, there's that. Okay. So which follow the net force it feels? All right. So here, what are the components? Right. So here there is a normal force, and there is a force of gravity goes down here. So this is force of gravity. The horizontal part here is going to be defined as mg cosine theta, and here it is defined as mg sine theta. Okay? All right. What you want to determine here is the force that it feels. The only force, so normally there's like friction here, but this is probably frictionless, so there is no force of friction here. Okay, so this goes away. This is horizontal, right? So the net force that it feels, so this is how it should look like. Okay, so F net is equal to MA. Okay, and then you have here force net. So all your forces, you have force normal. You know what? Let me just use N for normal. Then you have your minus mg cosine theta. Then you have plus mg sine theta. Then you have minus force of friction. That equals to ma. But watch all the cancellations that occur. Okay. There's no force of friction. This and this cancels each other out. So all you're left with that it experienced on the ramp is an mg sine theta equals to ma. This is the gravitational part, the gravitational sine part of gravity has two components here, a sine part and a cosine part. The only thing causing the object to slide down the ramp is the sine part. Okay? And that equals to ma. Right? So what you need to determine here is which of the following best approximate the net force. So you want to look at the net force here. So that's what they're looking for, force net. So the force net in this scenario, it's just this. So you're not even looking at MA, you're looking at F net. So this is the only F net here. So you need mass, gravity, and sine of theta. So your mass is 2 kilograms. 2 kilograms, okay, times gravity, which is 10, times sine of theta. But what is theta here? Some of you are like, what? This is why they give you the height and the hypotenuse. Okay, what you have here is, if you think about your trig ratio, okay, if this is theta, this is A, B, and C. Okay, your sine part is the sine of theta is defined as B over C. Your cosine part of theta is defined as A over C, and your tan part, theta, I think it's B over A. Okay, all right. So, but notice you have your sine part right here. It's just B over C. So B is 5. So the theta in of itself, this part, breaks down to just B, which is 5. This is B. And the A part, the C part, which is 20. Okay, so now you can just plug in this to a calculator. You could just enter this in the calculator if you want. 1/4. Okay, and this should get you roughly 5, and this is a 4, so it's newtons. Okay, this is off. It should be A. It should be 5 newtons. Okay. All right, let's take a look at this. Number 4. A 20 Newton block is being pushed around a horizontal on a horizontal table by an 18 Newton force. If the coefficient of friction is between them is that, find the acceleration of the block. Okay, cool. This is just a horizontal surface, so it's going to be very smooth for us to do this problem. Okay, let's just set up the block. Perfect. All right. Okay, so here we have some forces that we can draw. Okay, this is our a 20 Newton block force. Ooh, that's interesting. So here we have force of gravity, which is equal to 20 newtons. Then we have a force applied. Do we have is being pushed across a horizontal surface at 18. Yep, 18 newtons. This is your force applied if you want to see that. There is a force normal. And there is a force friction. And it moves, right? So again, if you want to be stingy, you can put force of friction kinetic because the object is moving. Okay, so they're asking to find the acceleration of the block. Okay, so here you could start from the acceleration is equal to F net is equal to m. If you're wondering how I get that, it starts with the original F net is equal to ma. Okay, this is Newton's second law. Okay, but you can do the algebra to get to here. Okay, the forces that you have, force normal cancels out with force gravity. The only thing you'll have is here. You have force applied minus force friction. Okay, force applied is don't plug in anything yet. So force applied minus F force of friction kinetic, so you need your mu kinetic times your force normal, but you know what your force normal is. Your force normal is mg. Mg here is just 20, so 20. So again, this is just mg. Okay, but you know what is force applied? That's 18. What's mu, which is 0.4. mg together was 20 newtons. Okay, again, I just didn't want to make the substitution so you could see how it looks like algebraically. This is how it looks like once you start plugging some values. Okay, once you plug that in there, you should get A is equal to 5, and this is meters per second squared, so it is C. Okay, number 5, the coefficient of a static friction between a block and a ramp. The ramp inclines is 30 degrees. If the block is placed on rest, the block will do which of the following? Okay, this is a very interesting phenomenon to happen. To see. Okay, we could talk about this. So let's talk about this question a little bit before we move on. Before I give you the answer. Okay. So here's this block. Okay, and this is 30 degrees. All right. Originally, it starts like this. Okay. Originally, it's like this. Okay. Now, here, what is the theta here? Here, this is when theta equals to 0. Okay, because there's no theta here. All right. Okay. So here you can write certain things. Here, cosine of 0 is just 1, and sine of 0 is, I think, 0? Yeah. Okay. Yep, that's right. So here, the static coefficient between the blocks and the ramp is 0.5, and the ramp inclines as here. What would happen to the block? So normally, right, again, you could draw all the other forces. Okay. So here, there's force normal. Here, right. Here you have force gravity. Here you have force gravity sine of theta. And you have right here Fg cosine of theta. Okay. And this is, there's something holding it back. So force of G. If you set up the force net equation here, and you want to see what the acceleration is, so if you set up the force net equation, watch what happens. So let me set up the original force net equation. So F net is equal to ma, right? What are the forces that you have here, right? The normal force would get canceled out with this force, okay? There is only the sine part and the force of gravity part. So you have force, I'm going to color code it for you. So you have force of gravity, the sine part, and you're going to minus the force of friction, okay? And then this is going to be equal to something, okay? All right. So, but we need to know what force of friction is. So watch how the substitution works, okay? So this force of friction is mu mg, right? Because it's force times, here, I might be jumping 2 steps. Force of friction is mu n. What is the normal force here? The normal force is just Fg cosine theta. Another way of writing Fg cosine of theta, okay, please note Fg, force of gravity of cosine theta, is the same thing as just writing mg cosine of theta. Okay, I just want to be very clear, right? So the normal force becomes mg cosine of theta. Okay, rewrite everything and you're going to sort of see what happens here. Okay, equals to ma. Alright, treat this equals to 0. Okay, treat that as equals to 0. I'm just going to stop color coding it now. You should sort of see where things fall. Okay, so Fg can just turn into mg, right? That's force of gravity. Sine theta minus mu mg cosine of theta. Watch the substitution that occurs. I want to add this to this side. So I have mg sine of theta is equal to mu mg cosine of theta divided by mg cosine theta divide mg cosine of theta. Mu is equal to mg gets pulled out. No, mg gets canceled out. We have sine over cosine. Sine over cosine is defined by tan of 0, tan of theta. So the coefficient of kinetic friction on a ramp is actually defined by this, the tan theta mu. Okay, so you could actually just plug it in. Okay, all right. So, okay, so the force of friction is, so here, oh, this is when it balances out. Okay, it balances out, but here you want to see what happens. Okay, at 30 degrees, okay, so you can just plug this in. So this is when it balances out, okay? So at 30 degrees, so at theta equals to 30 degrees, okay, you can just now plug in the values. Let's see if I can pull up decimals. You would have to do sine of 30. Let's see. Let me grab a calculator. If you put sine of 30 in your calculator, something should occur. Okay. So right here at this step, I'm gonna do something here. Okay. So you don't know if it's equal, right? You don't know it's equal. So you have mg. So you have your mg sine of theta is, you don't know what goes into the box, but you know that equals to mu mg cosine theta, correct? So again, you can ignore the mg, they both cancel out. So the only thing you care about is the sine theta part and the cosine theta part with the mu. Okay? So take this out, put 30 right here. Take this out, put 30 right here. What is sine of 30? Let's see, sine of 30, which is 0.5. What is mu? Mu is 0.5. So the mu here is 0.5. And what is the cosine? Cosine of 30. Oh, times 0.866 times 0.5. So in short, once you do the math, okay, you get 0.5 parenthesis box 0.433. You know that this is much bigger. So you would say that the this force, the mg sine theta part, is greater than, right, the mu mg cosine theta part. Okay, so what that means, so what's the answer? If this part is greater than this part, that means the force pulling it down is greater than the force of friction. So the answer would be it accelerates down the ramp. Okay, good. So here I only set it equal to 0. Okay, because I was trying to compare the two forces, and I do not know if it's equal, less than, or greater than. That's why I put an empty box. Okay, this is how you can compare and contrast them. All right, number 6. Assume a frictionless mass pulley determine the acceleration of the block once they are released. In short, you should already have this memorized. This is a simple Atwood calculation. You should have this memorized going into the test because this is a multiple choice, right? You have only so much time on the test. You should know this by hand. So I'll work through the deviation really quick. Okay, so okay, so here you have. Oh my gosh, why is it not going down straight? Here you have force of gravity. Okay. So force of gravity here would be force of gravity is equal to big M times G. Then you have this going down here, which is just force of gravity on this object, which is just little mg. Okay. Then there is a tension. So one of them has to be positive, one of them has to be negative. Okay. So I'm going to treat this as positive because m is bigger. So this is bigger. So I'm going to treat this as positive. So this has to be negative. Why? If you think about the direction of this, so this is positive. So anything up would be negative. So watch how it follows. Do you see how it follows the pulley? It turns this direction, so this has to be negative. Okay? Alright, so you have going up. Wow. Going up is the force of tension. Okay? And going here, going this way is also tension. Okay? This is minus, this is add. These two would cancel out. Alright, so what you have here is what is the acceleration here? So again, I'm going to set it up from A equals to F net is equal to the mass, but please understand it's the acceleration of the system, so this is mass of the system. Okay, so A of system is the force net. What are the two forces? The tensions cancel, so you have big M G minus little m G over what is the mass of the system. It is big M plus little m. Here you can pull out the greatest common factor, which is just a G. So you have big M minus little m times gravity divided by the summation of their forces. Sorry, the summation of their masses. So the answer would be this one. Okay. I'm going to throw something in here just for a little detail. Let's see. Let's say they threw in an extra mass here. Okay. Right. They call this MN. No. Let's call this M. Like we add another mass here. All you do if they added the extra mass, it's the same thing. Big mass here plus big mass. Subtract the little mass. Divide. Oops, sorry. So on top, it's still big mass plus big mass minus little mass. Gravity all over the summation of the mass of the system. So big mass plus little mass. Okay. Why are these two masses adding and not subtracting? Because they're all on the same side. These masses are all on the same side. So they're all on the plus side. Okay. Very straightforward. Okay. So this is a what if scenario. Okay. All right. Let's see. 7. If all the forces acting on an object balance, so the net force is equal to 0, the object must be at rest. Okay, this question is somewhat true. This is true-ish. What I mean by true-ish is that there are two types at when a equals to 0. You could have constant velocity, and you could have a equals to 0, where you have v equals to 0. You have a equals to 0. This is when it's at rest. Okay, so this is not always true. Okay, not always true. The object speed will decrease. This is when v equals to like negative decrease to like -2 again. All right, sure there's constant velocity, but right, it's not always true. It can be the other way around. The object's direction of motion can change, but not its speed. Okay, the object direction change. If you ever have this, the direction object change. So if the direction change, this means there has to be a acceleration. Why? Right? It's like in the centripetal. When we talk about circular forces, notice how the v here is always changing directions. Okay. The fact that it's always changing direction, there is a acceleration inwards. So there's also a force centripetal inwards. So this is completely wrong. The only correct answer would be none of the above will occur. Okay. I understand it's a long video, but I want to go over this in complete detail so you could understand it. A block of mass m is at rest on a fictional horizontal table placed on a lab on the surface of Earth, an identical block, blah blah blah. Has a bunch of information, but it's really stupid. So on the AP test, you have to find a strategy to read just the necessary information. So a block of M is at rest on a fictional surface, horizontal, place, blah blah blah. Read the question first, okay? Given that G moon is 1/6 of G Earth, the force necessary to give the moon bounce block the same acceleration A across the table. Wait, what? Did they just say this? Block? Did they really just say this? Block give the block the same acceleration A across the table. That's not an error. Wow, wow, that's not even an error. So what they're talking about is there's a horizontal surface, okay? There's a block, all right? And they want to know what is the gravitational force. So these are all, hopefully you see that. These are all, this is the force of gravity here. Force of gravity. Force of gravity is always downwards towards the center. So what I mean by that is, like, you see how we're on the planet Earth, okay? All right, and we have a force there's a centrifugal force down the center. Here we are. So here's the surface. Here's the block. Do you see how it's going down, down? But please understand it's going towards the center of Earth, but it's always pointing down. Okay, but it's looking for a acceleration across the table now, but it's asking for a. It's looking for an acceleration across the table, right? A lot of people will actually think number 8 is this one, but it's completely wrong. Okay, people think it's this one. It's 6. No, it's completely wrong. They also think it's 1/6. No, it's not this. It's F. The reason why is because force of gravity does not affect the horizontal. So across the table, this is horizontal, right? The force of gravity does not impact it, right? The horizontal motion across the fictional table is unaffected by the vertical gravitational acceleration. It would take as much force to accelerate the block across the table on Earth as it would on the moon. Okay? If friction were taken into account, then there would be some change, but here, right, it's not. Okay? If there is friction, there would be less force here. If there is friction, okay, if there is friction, the answer would change. If there is friction, okay, and friction is is equal to mu Fn, the normal force means there is a mu mg. Okay, so yeah, mu mg. So of course it would be force of friction would depend on the gravitational field, but currently it doesn't, because here this is a frictionless table. So the answer would be C. It would be B if there is friction. A as or A would also be possible. Okay, but currently it's frictionless, so it's just F because it's going across. Friction has nothing to do. Force of gravity has nothing to do horizontally. Okay. 6. A crate of 100 kilograms is at rest around 4. The coefficient of static friction between the crate and the floor is 0.4. The coefficient of force is blah, blah, blah. Which of the following is true? Wow, that is very interesting. Okay. So let's look. Let's just draw this out so you can see Here's the surface. Whoop. Here's the block. All right, so let's see what we have. Mass is 100, so oh my god, it's still not going down straight. Okay. Here you have force of gravity, which is equal to mg, which is equal to 100, 1,000 newtons basically, because g is 10. Okay. Do you guys understand that? I basically went 100 times 10. Got to be 1,000 newtons here. Okay, is at rest, blah, blah, horizontal. The coefficient of static friction between the floor is 0.4. That's interesting. So, force of friction, okay, that will equal to mu n, which is equal to mg, okay, which is equal to what? 0.4 parentheses, and mg was 1,000. So, what is this? Let me grab a calculator. I know its exact value. 0.4 times 1,000. Oh, 400. So force of friction is equal to 400 newtons. All right, and then we have a force applied of 344 newtons. Okay, yeah, the object's not moving. Okay, the force applied is not strong enough to overcome the 400. Okay, so I want you to understand that for the object to move, force A, if you want to be picky, this is static friction. For the object to move, Fa has to be greater than force of static friction, right? Which is okay. So which is in this case 400 newtons. Okay. If the object has less mass, then yeah, the gravity can. If you cut the mass of the object in half, right? If you cut this in half, it will probably be like 500 newtons. If this is 500 newtons and you plug it into here, so this is if. Hold on. So the answer here, okay, before I do my what if, is this: the crate will not move. Now, let me give you a scenario that it would move. Okay, what would be the mass for it to move? Okay, listen very carefully. So right now, let's look at the math. Right now, there is a force applied, okay, of 344, and we need a box here. We want it so that this is greater than this number. This number has to be slightly under 344, okay? So we have mu, which does not change, and we have force of gravity. So 344, right, needs to be slightly bigger than this. Mu is automatically given as 0.4, and gravity is automatically given as 10. We do not know what the mass is. This 0.4 times 10 is just 4. So 344 is greater than 4m. Okay? So divide this by 4, divide this by 4. So m, so 344 divided by 4, this is 86. Okay? So I'm just going to flip this around. Commutative property. We could say the mass has to be, it cannot be less than or equal to. This less than or equal, if it has equal sign, it means it's at equilibrium. Okay? So, oops, sorry. So mass has to be less than 86 kilograms to move. Okay? Move, a better word, to overcome static friction. I think that's a better way of saying it. Okay? So the purple stuff here is just a what if scenario, okay? This is just a what if. Please understand, this is just what if. This is a what if, okay? This is a what if. This has nothing to do with this question, okay? It has to do with this question because I gave us an other way this question can be asked on the test, okay? But as of right now, it's the crate would not move because of this explanation. For the object to move, Fa has to be greater than 400 newtons. Because why? Force of friction is 400. The current applied is 344. 344 is is smaller than 400. That's why the crate would not move. Okay. Here's the last one. 10. The two crates are stacked on top of each other on a horizontal floor. Okay, I think here. Let me just draw this out. So here you go. Here is the first crate. And then here is these. Hold on. Crate 2 is on top. Both crates have the same mass. Oh, they have the same mass. So let me try to draw them with the same mass. And here we have is on bottom. So this is number 1. And this. And this is number 2. And compared to the strength of force 1 necessary to push only crate 1 at a constant speed across the floor, the strength of force 2 necessary to push the stack at the same constant speed across the floor is greater than F1. Okay, this is interesting. So here they say they have the same mass. So you would say the weight of crate 1 is greater. That makes no sense. The weight of crate 1 is the same thing as the weight of crate 2. Okay? Because they have the same mass. Okay? So this one makes no sense. The coefficient of static friction between 1 and crate 1 and the floor is greater. Is compared to the strength of force 1, blah, blah, blah. The strength of force 2 necessary to push the stack at a constant speed across the floor is greater than F1. So Y is pushing F2, okay, require more force than pushing F1, right? So with crate 2 being on top, the force pushed down on the floor is greater. So that means that the F of gravity of the system, right, is this goes down. Let's just make this like 10 kilograms, right? 10 kg. The force of gravity pushing down is 100 newtons. This one is also pushing down at what? 100 newtons. So the force of gravity of the system is 200 newtons because it's both of these masses together. It's the same thing as if I said there is one object that weighs 20 kilograms. You could say that goes down at 200 newtons. Okay, I treat the two crates here as one system, one object in this system. Okay, so here this one wouldn't work. Okay, so the normal force exerted by the floor on crate 1 is greater than which increases the frictional force. Okay, because remember the force of friction is defined as mu n, which is equal to mu mg. Okay, this all depends on the mass and the gravitational force. Okay, so the n will be greater on force 1. Why? Because this one that is going up, right, force normal is greater than, okay, is greater than force 1, because here the force normal here is different from the force of friction of the force of normal for the crate. Okay, so this is off. All right. Okay. It has nothing to do with coefficient of friction. If this doesn't make sense, you could also do a process of elimination. The crate wouldn't make sense. We know the coefficient of friction between the 1 and 2 is not greater because B, if D is wrong, so is B, because they're mentioning the same thing. The coefficient of friction between crate 1 and the floor, that is essentially the weight. Okay, the coefficient of static friction between 1 and the floor is greater. Not quite. It wouldn't be greater. If it would be greater, that means crate 1 would require more. But it is the normal force that is on crater 1 that is greater. Okay, that is the reason why when you push, the strength of force 2 is necessary, going to be greater than force 1. So here, this is force 2, which is going to be greater than force 1. Okay? All right, so there you go. I understand that was a lot of information. Um, Hopefully, you can dissect all that information. I try to be as clear as possible. Go back, look at the videos, but those cover a lot of pieces. Okay? So those are all your solutions.